This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Our next speaker is Farhad Farokhi from the University of Melbourne.
Thank you. Okay, I'm going to talk a little bit about solving problems using quantum computing, and the first step is to encode your data into the quantum computer. It's kind of essentially is going to show you if you make the setup of the problem large enough, the answers becomes quite trivial. So it might be a kind of cautionary tale of if you make it too general, then you might not get anything interesting. But in the way, hopefully, we try to learn something meaningful about the smaller kind of problem setups that might be interesting to kind of look at. So if you have some kind of problem that you have two random variables essentially correlated or jointly distributed with each other, and somebody gives you the X and tells you, guess me what was Z is, that's the classic setup of your statistical inference problems or machine learning problems. You get a bunch of features and you want to tell what's the class of this data is. So what you can do is encode, if you're from the community of people who like to do quantum machine learning, you can encode your data into some kind of quantum state, do some kind of computing, take a measurement, maybe even do some kind of post-processing on the end, and make a guess. And you would want to make sure that the guess that you're doing at the end is going to match the guess that you don't have access to. That's kind of ground data, the real thing that you want to try to estimate. So I'm going to make the problem setup a bit easier to try to understand. So I'm going to assume that this X is a discrete random variable. It can be very large, but it's discrete. We know it. This Z is also a discrete random variable. We don't know it. And it's the outcome of the inference. This is Z hat is our estimate. And we are interested in understanding what kind of encodings would make sense. There is lots of different encodings out there that people have tried to work with and heuristically check them and see which one's making sense more or not. So I want to see if I were to turn the problem around, trying to understand it from an information perspective, would I be able to get to some of those things, or would I get somewhere quite weird? So think about it from that perspective. The channel that you can have here that you're using for quantum computing could be any arbitrary thing. So you can imagine if we have the ability to implement whatever we want, what's the best thing that I can do in terms of the encoding if I fix everything else, I don't worry about them. And also the class of the measurements that you can take is whatever general kind of class. That's a class of POV measurements. And there is no restriction on how much computational power you have in the classical side. What you can do with the data you get on the other side. You can do whatever you godlike. The measure of success for you is to make sure that this Z hat and Z match each other. So you want to increase the probability of those instances occurring for you. So what you can show that is that the probability of getting a correct answer is upper bounded by two terms getting multiplied by each other. One is essentially the quality of your encoding. How would you go ahead and encode these X's into this states row? And this calligraphic Q here is what's called the maximum leakage, which is very similar to accessible information. For people who know accessible information, it's the when you take a maximum over all the possible measurements that you can take of mutual information in case of accessible information. But here we are taking best kind of measurement over a different notion of information. After Shannon came up with mutual information, a couple of gentlemen tried to extend it to a more general setups, one of them being Alfred Rainey, the other one being Robin Simpson. So this term in front here is the Simpson information, which has a lot of nice properties, and information theorists have looked at it quite a lot. So it's like if you pick up accessible information and change the mutual information to something that's a little bit more useful in the context that we're going to talk about. So this is that Q, and then this other side is something that's inherently unrelated to what you're doing with your quantum computer. It's something that's really related to the problem that you are trying to solve. how easy it would be to, without knowing anything about the x, guess the correct answer. Of course, some problems are very trivial. Z could be always equal to 1, so in that case, you don't need to do anything. So your problem is very easy to solve. Some problems are harder because you might have a uniform distribution prior without knowing x. And in those cases, it would be harder to solve the problems. So these two terms get multiplied by each other, and they give you an upper bound for this, probability of having this accurate thing. And the same way that you have a lot of nice algorithms out there to compute the accessible information, you have algorithms that follow the same similar kind of steps and gives you this, maximal information leakage value. The good thing, another good thing about this inequality is that this inequality is tight. There is an instance of your statistical inference problems for which you can attain this inequality, okay? So, think about it as a cat and mouse game. I can always make your life very hard or very easy by trying to come up with an optimization problem that saturates this upper bound, okay? Because this is possible, and if you want to try to come up with an encoding here to construct this state that is universal, that's not thinking about what's the underlying statistical problems that you want to solve, then it might be useful to try to think about maximizing this upper bound and seeing what the behavior of this upper bound is. Because first of all, for a lot of problems, this upper bound might be a good measure of how accurate you are. At least it gives you an upper bound of how accurate you are. If this upper bound is very small, then you know that your accuracy is not going to get anywhere nice. But we know that for a category of problems, it's even more than one problem. There is a family of problems for which these upper bounds get saturated. So there are possible to construct problems that you would need to be able to deal with this and try to maximize it. Now I'm going to take a very long bow and try to do something that's not necessarily scientific, but bear with me for a second. If I try to deal with this upper bound and try to find another upper bound that's no longer it's in the form of this information, but it has something else about the dimension of my problem, you're going to see that this probability of being able to give you an accurate estimate of Z is become upper bounded by how difficult is your problem to solve, and a couple of parameters that relate to the dimensions of your problem. One is the dimension of your random variable x. How many possibilities are there for random variable x that you got? Because it's a discrete variable. The other one is the number of the qubits that you got, okay? So the dimension of this Hilbert space that you're encoding the states in, which tells you how many qubits you got. There's a multiple of 2 behind that. So logarithm of it would be the number of qubits, so twice the number of qubits. Again, this inequality also gets saturated for at least one problem. There is actually a family of them because you can rotate them around in a nice way and construct a family of them. So if, this is the long bit, if I know that this problem is going to get saturated for 1 qubit, I don't want this upper bound to be unnecessarily small. What does it mean to be unnecessarily small? If I make this number of qubits quite low, to be smaller than this, then the upper bound is getting saturated by resources that I've got. So that's an artificial saturation coming from my resource availability. So I would guess that maybe if I were to select the number of the qubits to be large in the order of the cardinality of the x, then I'm not dealing with unnecessary constraints that are coming from the number of resources that I've got, but I'm dealing with the difficulty of underlying problems to solve. And the difficulty of underlying problems to solve is getting encoded by this variable here, okay? So if I have enough resources, I would be able to push my boundary and try to do something better. Not surprising again, okay? It's very trivial in that sense. So if you want to construct a universal encoder, you can pick up this upper bound that you got here, that you know that it's going to get saturated, and say, okay, this is a measure of information. If this measure of information that I've got, then I can try to maximize it to construct these encodings of the state that gives me the most amount of information. And I try to solve it. Now, why do I think about this in terms of a universal measure of information? Because first of all, if you look at this guy, this is not a function of any of your underlying probability distributions, okay? It's not a function of probability of Z. It's only a function of probability of X in terms of the support set of the random variable that you got there, okay? It's not a function of your quantum computing algorithm. It's not a function of your, static, classical post-processing part. It's not a function of your measurements. So this is what you're getting. You're trying to maximize the amount of information that goes through the circuit at the beginning, and then what you would do to it at the end is just going to reduce it, because you have post-processing inequality. So you're going to try to maximize this to construct something that's universally, hopefully working good for you all the time. And that's why you think about it as a, some kind of universal solver. So one first thing that you would get is that the maximum of this guy is always going to give you pure states. So p-encodings by pure states would give you the maximum. You might get the maximum by non-pure states, but the pure ones are as good. You get another thing, which if you have enough resources in your quantum computing platform, then the best encoding that comes out of this becomes your usual basis or index encoding, okay? Again, not surprising. And this is where the generality of the problem setup comes into the picture. I have a very arbitrary statistical inference problem, okay? There is always one problem in that set of statistical problems that's very difficult to solve, okay? And for that very difficult problem to solve, you need to be able to construct these states in such a way that you would be able to get the maximum amount of information out of them and don't lose anything. And this kind of index encoding comes into the picture because of that very particular problem that's very difficult to solve, okay? Because from the beginning I had this very generic setup, now I'm getting a very generic answer. But if I don't have these constraints, and if I don't have this many qubits, if I'm not as lucky, still this guy is giving me an answer, and that answer is a useful answer. Because that answer is that the maximum amount of information that I can potentially push into this circuit at the beginning, so that at the end what you do is result in something useful, okay? But in those cases, there is no closed form solution. You need to be able to try to solve this using some kind of subgradient ascent and trying to get to the optimal solution. But that gives you some kind of a measure of how you would be able to construct these encoding sets. So you get something that has maximum amount of information for you, so you do something to it at the end, and then you'll be able to get the answer out of it, okay? But again, if you have enough resources, encoding them with this specific kind of encoding is useful. And again, that also hints at the fact that there is a problem that probably needs to be solved using a classical circuit. And this kind of encoding becomes very useful because then you can run a classical algorithm at the end of it, okay? And again, this is an artifact of a generality of the sets of problems that you want to be able to solve, okay? If you restrict yourself in sets of problems that you're going to solve, this is not going to pop up, okay? So it kind of says a little bit about if you want to solve a problem, it's good to try to study the underlying architecture of the problem, the kind of problems that you have, because if you go for a very generic problem, you're going to get very generic answers that are not that useful. So the way that, what I wanted to get from this is that, that Q, calligraphic Q, is a very useful notion of measuring information. It kind of extends this mutual information and kind of considers this worst case, all kind of problems category that are very useful in some scenarios. They are useful for understanding security. They are very useful, for instance, in Shannon cipher channels and so forth. Also, they might be useful if you want to consider a family of problems and talk about encoding over a family of problems. But because those sets of problems are so generic, you might get something that might be a little bit stupid. For instance, basis encoding might become optimal if you have enough resources. Again, because the problems are so generic, you're going to get that kind of problems out of it, okay? An interesting thing would be to see for a practical problem and when you don't have enough resources, what kind of, encodings pop out and what is the structure of those kind of encodings. So this gives you a measure of being able to compare them with each other and trying to reason about them a little bit. So that's, I guess, a very short view of what I wanted to say in 14 minutes. Thank you very much.
Thank you very much, Farhad, for keeping to time. Now, is there any questions from the audience? Yes.
Hi, thanks. That was very clear. How should I think of how should I think of this in context of no free lunch theorem? So you set out the problem of how to solve every possible problem, but this is an ill-posed question to begin with because we know that's not possible. So this is a tension. How should I resolve this tension?
I mean, yeah, so if you set up the problem of solving every possible problem, you can always construct one problem that makes you a lot of trouble, and then solving that requires you to encode everything possibly. The way that you can resolve that by restricting the set of problems that you want to solve, and then that would changes the supremum that you have in the inner side that I didn't show you, there is in the paper, and that would kind of changes this notion of Q tilde and a little bit massages it into a form that becomes much more amenable to your problem. And then you can try to maximize that one. But that would essentially means you're adding a constraint over this optimization of all the problems that you want to solve. How easy is it going to be to solve it might become as hard as solving your original problem. So because this sets of problems is so generic, dealing with it is easy, and that's often the trick in information theory. If you kind of make your problems become general enough, you might be able to say something interesting about them, but then you might lose the, some other aspects.
Thanks.
All right. If there are any more questions for Farhad, I'll get you to catch him in the break. So to keep to time, if everyone could thank Farhad again.